This is the screencast for section 9.4, example 8, graphing a sequence defined explicitly. Well, arithmetic sequences have a common difference. So that means you start out with a constant and then keep adding the same number over and over and over again, which you may have predicted would create a linear graph. The slope would be the common difference, the y-intercept would be your a sub 1 term. A geometric sequence, the terms are defined by a common ratio, which is like an exponential function. Depending on what that ratio is, it might be exponential growth or decay, but you have an a value, your first term, and you multiply by your ratio to the whatever power, depending. So we'd like to take a look at some graphs of sequences and what other shapes they might produce. I mean, basically a sequence is taking specific entries in a graph and plotting them as points. So in method 1, you can make these a sequence into a scatter plot. First, you can enter, go to your catalog button on your calculator, which is second 0. And then alpha is already pushed. So then go to the letter S because you're looking for sequence. And you're going to have to arrow down for a little bit, but you'll see SEQ with parentheses and without parentheses. You want the one with parentheses. That one right there. You're going to use that function to tell your calculator to put in the numbers maybe 1 through 10 into list 1. So you'll put SEQ parentheses and then x, x, 1, 10. So it's going to enter the numbers 1 through 10 in list 1 because you'll then store that as list 1. And you should get a list of those numbers then below after you hit enter. Then after that, you can tell your calculator to take every entry from L1, square it, and then subtract 1, which is what your sequence has been defined in the original problem. And then we'll store those into L2. So now L1 has your basically number of entry, first entry, second entry, third entry, your K value. And then here is what happens to that value. So these are explicitly defined. And then I can turn the plot on. And I chose zoom stat because these are like I'm entering statistics. And I can see that the graph turns into a half of a parabola, as I had predicted it would from the original equation. Now the other method of graphing sequences in your calculator would be using sequence mode, and you can go to mode and then over to sequence here, which is what the other, the SEQ does in your catalog. So we'll change the sequence mode, and then in y equals, you can type in your n min, which is 1 in this case, and then I can type in my u of n. So my function, my sequence u, dependent on its nth term, would be n squared minus 1. And the first term, so this is u of my n min, so u of 1 equals 0, because 1 squared minus 1 is 0. And I hit graph, and then I chose to zoom fit for this one. And you can still see that parabolic shape. The entries are all correct. So that would be a second method to graph sequences. The now try problem number 33 asks us to graph a sequence. Since sequence, I did it in both ways. I chose sequence XX, 1, and I chose 20. Let's go up 20 entries, and I stored those into L1. And then I typed in 2 minus 1 over the L1 values, and I stored those into L2. And then I plotted, and I get this graph that is 1 over x flipped over the x-axis and then shifted up 2. So it should have a horizontal asymptote at y equals 2, which it in fact does. And then here it is in sequence mode, the same idea. Same graph, same entries. You can also adjust the window by hand. You don't have to use zoom fit or zoom stat. You can adjust by the window by hand by going into window. It just depends on what best fits the situation.